We are not in a high number here. Well, okay. So let's wait for a couple of minutes for other participants. And I switch off my camera too because I have some technical problems because it is switching off itself. Well, so what you can see is, let's say, invitation list to this action, to this seminar. It is organized in the frame of online seminars of a project called R2P2. The name is quite complicated, but you can read it below on the sheet of this paper. Today's seminar is focusing on application of robotics in the construction, and just because we are solving this problematics or this topic at Technical University of Liberec in a frame of other project called 3D STAR. Here you can see abstract or abstract of the topic of today's seminar. Unfortunately, we are going to present only in two persons, me and my colleague, Dr. Hubka, Associate Professor Milan Kolář has other activities. But we have, I think, all information for you. Well, let's start with the presentation. So I will run it. So do you see the presentation, please? Lukáši, do you see it? Or anybody else?
Yes.
Yes, excellent. And if I switch to next slide, does it change?
It's working.
Excellent. So welcome here one more time. What is waiting for us today is has this content or outline. At first, I would like to introduce a project 3D STAR, which is solved here at Technical University of Liberec and at other universities in Czech Republic. Then I would like to go to the topic quite general, 3D printing in architecture, which has subsections, let's say 3D printing technologies in construction, 3D printers. I have mistakes here. Then materials for 3D printing in architecture, 3D printers for construction, and then briefly about inspiring projects for our purposes. And I finished this section by sorting of robotic construction or construction robots from the point of view of their autonomy. The other part of the seminar or my section is will finish with project contemporary results, what we've got from the project 3D STAR up to date. Then we change our roles with my colleague Dr. Hubka, and he will present the topic navigation in 3D printing of buildings. So this is our research part in the frame of this project. After his presentation is coming summary and discussion. So let's jump in the topic briefly about 3D STRA project at TUL. Unfortunately, this project is not so well known at Technical University of Liberec. The reason is is discutable, but let's go and present it to you. So 3D STAR project, 3D STAR is an abbreviation of Czech, its acronym for Print in Civil Engineering and Architecture. So this project is co-financed or supported by EU funds, and is solved, and it is going to be solved in period from 2018 to 2022. So we are behind the half of the project right now. It's a collaboration between, or it's collaboration of two institutions. One main institution is Technical University of Liberec, and the second institution is Klockner Institute at Czech Technical University in Prague. So it's a quite complex project. So there are lots of groups. They are focused to specific domains, not robotic and navigation as we present here, but also to material science, machine engineering, research, and so on. The task of this project is as follows. So propose new approaches in our architecture. So from the point of view of objects and from construction parts, then design of a robotic 3D printing system for on-site construction 3D printing, and of course to develop appropriate 3D printing material, which is not on the market right now. What you can see on the right side of this slide, it's a let's say architecture. It's a building, one of many trial houses, which can demonstrate the advantages of 3D printing, 3D printing technology. Unfortunately, it's in Czech only. Also, the web pages, but it changed very quickly, I hope. Let's switch to another slide and go to the general overview about 3D printing technology or additive manufacturing in construction. Why 3D printing in civil engineering and architecture? Well, the reason is quite easy. This kind of industry is following the same trends as machine industry. So they'd like to accelerate the production of or building houses. They would like to save also material and waste. They would like to be cost effective. So in this domain of industry, and this kind of technology support or enables innovative design in structures. So, and probably you know the term Industry 4.0. So there is also construction 4.0. This trend is visible also in the market. What you can see on the right side is the part or semi-final or semi-finished building, the largest building 3D printed building in the world up to date. So this is a building in Dubai, and it was built by this robotic system, by this arm by company Apiscore. Well, if we are in the topic in general, you can find also this very nice graph on the internet. It was made by one Dutch company, L Studio, and it maps the development of 3D printing technology applied in architecture. So you can see it's not so new technology. In the middle of 19th century, 90s of 20th century, contour crafting starting with first tests, and it accelerates in last decade, and we try to follow also this trend. And what you can see also in this graph is variety of input material, because construction use every imaginable material. So from concrete to salt, and you will see on following pages. And what is also visible from this picture, that the centers of research is split around the world. So there are no special regions who are interesting in 3D printing technology, but it's the lack for this technology is almost everywhere. What is missing here? South America, but we already have seen some projects from this part of world. So this should be also this picture could be also improved and up to date, but it stopped some in the year 2017, I think. Oh, well, I would like to remember previous seminars from my colleagues and me. These seminars were focusing on 3D printing technologies, let's say additive manufacturing technologies, which are situated at Technical University of Liberec and are used or applied for different tasks. So there were two seminars held by Dr. Shafka and Dr. Ackerman, and then one seminar I had 2 weeks ago. The topic was quite different to today's topic, but it's the same in the theme. So the additive manufacturing was used, and this is the important, let's say, keyword. Well, I mentioned here that 3D printing is not pure synonym to additive manufacturing, but well, we can deal with this. What I would like to mention on this slide is these 7 groups of or categories of additive manufacturing, because in construction segment or 3D printing, it's not so standardized as in industry. As you see, it's already standardized by ISO norm or standard, and it's divided to 7 categories, which are very nicely presented here on this picture. And probably all of you know these abbreviations, SLA, DLP, and so on, or FDM, which is quite more popular than these basic groups like photopolymerization, material extrusion, material jetting, binder jetting, and so on. But I would like to use this picture to use this kind of categorization in 3D printers for used for construction. They could be all these printers. They use mainly plastic or metal or some powders, plastic powders. They could be also used the products from these printers in construction, but try to take a look on these problems from large scale. So to print directly whole houses. And from this point of view, we can find examples from projects from the world, what they projects they use this kind of special kind of 3D printing technology. So on the left side, you have these 7 groups, and I tried to find a large scale 3D printer with similar technology. So first, photopolymerization is from the large scale point of view is not suitable for printing whole houses or living houses or living or objects for living. So I haven't found, maybe you know some example, and I will appreciate if you send me feedback. But what is the most used technology is material extrusion. So there exists plenty of different robotic systems. They use this kind of additive manufacturing strategy. Another one, it's not so material jetting, used for 3D printing in construction. I found only one project. They use so-called shotcrete. It means spraying concrete, and it's also on a robotic arm or on a robotic printer. Then what is used binder jetting, let's say, you can find sand 3D printing or GIPS 3D printing. Then powder bed fusion, material sintering, sand. There are some interesting projects from deserts or placed in deserts where the sand and sun is in a lot. So they try to sinter on site this material by sunlight, focused sunlight. The 6th category, direct energy deposition, is also, you can also find on a large scale. There exists the metal 3D printing. One company from Holland, from Netherlands, use this technology for printing whole bridge, for example, or topologically optimized objects. And the last, sheet lamination, I haven't found any example of this kind of technology which is used for 3D printing of houses. What is here? It's a question maybe for the discussion. What does it mean, bricklaying? Because if you have small particle like a brick, is it a 3D printing and additive manufacturing? It's a question for the discussion at the end, because I was asking about the same, and I was thinking about Lego bricks. Is it also additive manufacturing technology if you put these small tiny bricks together? Well, we will see at the end of this presentation. Let's move a little bit forward to materials. As I presented on the slide where was the picture with different projects and with different materials. So you can find living or objects for living printed by 3D printers from different materials. So at first from concrete, then clay or mixture, then plastics. Artificial stone is used also, sand, metal, nylon, salt, and a mixture of everything or of mentioned materials. On the right side, I was wondering if there exists also really a salty house. So you can see the igloo, let's say, printed from salt material. I don't know if is it possible to use it outside, but yeah, it's a very nice architecture object. And from technological point of view, why not? Why not use this material? What was not and is not solved by table 3D printers and in industry is the question of location, because if you have such large scale objects to print, so you have to answer if is it possible to print them on site or off site. So in a company hall or in a fabric or prefabricated, and then carry this already printed house to the specific place by some kind of transport. So question of on-site, off-site. Then what is also not solved or not required on table 3D printers is a question of mobility. So these large-scale printers, they could be static, so like cranes or something like this around the whole printing area, or they could be also mobile, so tiny 3D printers. And if they are mobile, they can be divided in these let's say groups or categories, or to aerial vehicles, so flying objects, or mobile robots. They can move on the ground, or they can climb. On the right side of this slide, you can see this monster, but it's a very nice monster. It's the PhD thesis or the output of a PhD thesis from MIT, from Dr. Keating, and he and his colleagues designed this mobile platform with several arms. It's a crane arm and then a standard industrial robot, and they equipped this system by different printing heads. So, and the printing head here was used for foam spraying or foam extrusion. But this system can also work with shovels, or it can dig material or ground and so on. So it's quite a universal system. If you take a look on the left, so it could be used on site, and it's for sure mobile robots, and it should also handle with questions of navigation, localization, and so on. Well, we presented specific construction, but in a public or what you can meet mostly, they are standard construction in a XL scale. So you can meet Cartesian robotic systems used as a 3D printers, or cylindrical or spherical or SCARA or extended SCARA systems. Articulated, it means like angular robots or standard industrial robots, or parallel, let's say delta, call them delta system. What you can see on the right side is the XL very large delta or parallel 3D printing robotic system, which is used in a project called WASP. It's an Italian project, and they use also strategy of extrusion, and they use not cement-based mixture, but clay mixture with waste rice grains and so on. So here is the name of this picture, and there is a term used, matte. So they use matte. It's very interesting project. They use also spherical conception or robotic systems for printing. They use this in a recent project you can find on internet. Well, it's a quite complex task to answer all these questions, and we are not alone in our project. We are also inspired, not inspiring, inspired. We are inspired by different projects. We try to work on a table and follow, let's say, approximately 50 projects which are from academic or commercial sphere. Lots of them from the year, let's say, 2015 or 16, were discontinued, or lots of them rise and still continued. It's very nice to see the development and the strategy what they use. From the list, the most important from our point of view, because we are focusing on our mobile robotics and using these systems in construction, we can name APIScore or SAIBI or Construction 3D, Hadrian X from Fast Brick Robotic, or In Situ Fabricator from ETH, and many others. What you can see on the right side, it's a, let's say, holy grail, but it's one project which was discontinued or stopped several years ago. It was a project called CASA, mobile platform with a robotic hand, maybe very high level of autonomy, but something was going wrong, and it was stopped, this project. But it was quite inspirative from these pictures and videos. Here you can see pictures from these inspiring projects, robotic hand on a mobile platform from the company SAIBI, Construction 3D, a French company. They use also mobile platform with robotic hand, but not based on an industrial robot, but let's say crane arm. On the other picture, you can see In Situ Fabricator from ETH Zurich. They use this mobile platform with industrial robot for not only printing, but welding, for example, for bricklaying and so on. And they follow specific research tasks. other picture here is a truck with an arm. It's from the company Fast Brick Robotic. It's an Australian company. This robot is called Hadrian X, and it's suited for placing bricks. In this arm, there is a hole, or it's a, let's say, cable-driven belt, and it holds bricks to specific position, and it's a automatic robotic bricklaying robot. It's a bricklaying robot. And the last but is a recent picture from Apiscore. They presented a few days ago this new version of their robotic system. They place it on a mobile platform, and it's for 3D printing from cement-based mixture, and they have already some results, so you can find them also on the internet. Well, from this table of inspiring project, I made these graphs. So what you can see, what is, let's say, how is divided, how they are divided, this project, this following project, from the point of view of 3D printer location. So it's a, let's say, 50-50 off-site, on-site. But what is the question of system mobility? The 3/4 is mostly static. It's not equipped by any moving belts or wheels and so on. So, and the last graph I made or prepared is going from the fabrication technology. So the mostly used fabrication technology is extrusion. So cement-based or foam-based or mud extrusion is used mostly by these large-scale 3D printers. If we have an intersection in these all conditions, according to our projects, only 14% of these projects we are following or we are inspired, have almost similar tasks. So they use extrusion. They like to extrude cement-based material. They use robotic arms on mobile platform, and they are able to print on site the object. Well, I'm going almost to finish my part, but when I summarize recent results from our project, I would like to mention this very interesting slide about levels of autonomy in construction. I read it in a quite recent publication from Mellenbrink and Collective, and this researcher used standard norm or standard from the car industry, which is about driving automation, and use this strategy or use this categorization to autonomy in construction. Well, level of automation number 0, no automation, is widely used here recently on construction sites. So there does not, or the system does not control any degrees of freedom, even if it is capable of enhanced sensing. Then what is coming now, that operator assistance is necessary for automation or automated system on construction site. Then there exists also already some automated system where the partial automation is used. So there are some degrees of freedom of such systems, and they require also a human operator. What is not so well, the level of automation in construction, number 3, conditional automation. There exist some systems capable to operate in a high number of degrees of freedom. They are programmed, and they can call operator. But from this level, from the level of autonomy number 3 to 5, you can count systems, robotic systems on the market or in research papers or projects on one hand or on two hands. So they are not so very well finished, let's say. So high automation system can autonomously execute tasks under certain site conditions. This was research in the work of Mr. Keating from MIT, and full automation, the last level, doesn't exist, but it's a holy grail for space agencies, because they would like to have such a 3D printing or automatic system for building lunar bases or Mars bases without any operator. But it's still on a level of science fiction, let's say. Well, switch to the finish of my presentation, of my part of my presentation. I would like to briefly inform you about recent or contemporary results from our project. So let's mention the goals or tasks of our project. We'd like to design mobile robotic arm-based 3D printer. Let's say it could be the level of autonomy 3. So it's a quite nice, it's a very nice task, but there are lots of questions to be solved. So we'd like to extrude concrete or cement-based mixture, and we also would like to use this mobile 3D printer on site, so on a position where the building should stay. What we've done until now, or the groups from the project, we designed and assembled and run testbed. So it's a Gantry style or Cartesian robotic system for testing of mixture of the printing material. So what you can see on the right side, this is this CNC machine. It's placed in Prague in Koprnický Institute, because Koprnický Institute is responsible for material science, so development of a special mixture for 3D printing by 3D printers. So our colleagues here from Technical University, from the Faculty of Mechanical Engineering and the Faculty of Mechatronics, designed and produced this machine. What is another task is to design a printing head. So it was designed first, second, and now also already the third version. So what you can see here on the right side is a design of a first version of printing head, so which is placed then on this test bed. Nowadays, colleagues from Klockner Institute, they are testing to print some objects. They are prepared from our colleagues from Faculty of Architecture. So what you can see, this is the small chair here, and it's a nice starting point to get information from the behavior of material and from the behavior of this test bed. And during this operation, so we can also we can test 3D printing software, which is necessary for processing of all data from 3D data from objects to transfer them to the machine. Well, there are lots of tasks to solve too, so we will continue in research in all domains, so improve the software, mixture, and test bed. But the main goal of the project is to design the functional model, not functional mode, but functional model of the robotic system in scale 1 to 2. So what you can see on the right side is a design of this arm. It's manufactured now, and it will be present in 1 year, hopefully on a mobile platform with already solved navigation and localization tasks or questions, which is the next part of this presentation. Well, that's for the moment all from my side. I would like to switch and give microphone to my colleague Dr. Hubka, and he will present you or familiar you with the topic navigation and in 3D printing of buildings, which is our domain in this project. So Lukáši, it's your turn. So,
okay, thank you, Jan. I want to show you some or present you some actual technologies which are related to the navigation in 3D printing of buildings. Let's say the navigation generally in this area has two aims. The first aim is to localize the wool robot, wool machine, on the construction site. So to find the place in some constructions, it's necessary to solve really precisely this task, this challenge. In some other type of a construction, it's not so necessary to be so precise. Sometimes we do not have almost any restriction on this global position. I will show you during the presentation. The second task for, let's say, the measurement, navigation, localization is to know where exactly is actually the printing head. Because the printing head is the tool which relies finally the product. So we need to have such a information. Okay, so to my presentation, I want to start here with some let's say short introduction. The navigation methods generally are.
Lukáši, pardon.
Yes.
Have you we don't see your presentation. Can you show us?
See nothing. So I try it once more again. I'm sorry.
Excellent. Yeah.
Is it better? Yeah.
Yeah.
Sorry. Okay. So the navigation highly depends on the construction of the machine, because different type of a construction, as I told you, use a different approach how to measure the actual position of a printing head, how to measure the position of the device of the machine. And of course, then it's a question of some strategy, how to realize this measurement. If you use some combination of a sensor, if you focus to only one sensor. Another question is, of course, the accuracy, because in really close connection with the accuracy of the measurement is the quality of the final product. It's absolutely clear. If we want to move forward in the actual trend in the automatization of building construction, as Jan presented, so we need to also focus to such a task, because with the manufacturing, the accuracy is always questionable. But once you switch the mode and you go to the same problem with some machine, so you automatically expect that the precision and the accuracy will be on the next level, will be much more higher. But the accuracy, so the final quality, let's say, of the walls, for example, of the whole building, is not only a question of the navigation of the sensors, but of course it's some complex task, because you need to have a really good construction of the printer. You need a really good mixture of the concrete with adequate properties, and so on. So the navigation itself is only, let's say, one part in the whole puzzle. The last point here on this slide is what are the aims, let's say, because as I thought, we can have one object, which is important for us, only printing head, or two objects. So also focus the robot in a space. As Jan presented some approaches which are now actual, now in development. So all of them are, let's say, dealing with this problem. When where the robot is staying in one position during the printing task. I will show some, let's say, exotic solution where the robot is also moving, but then the navigation task is really very tough. For navigation, of course, we use, or is used, some industrial background. It's absolutely clear, because it's a pretty complex task, and it's important to use some solution which are working. The actual situation is that we have different type of sensors, different approaches, how to measure the distances, how to measure the position, how to measure the angle, because this, let's say, 2 or 3 factors are important for the 3D printing from a concrete. The, let's say, top level of the sensors with the precision which is in let's say tens of millimeters or much more higher sometimes, is a laser tracker. It's a really precise system. Here we have one picture how it can look like. It works for short distances. It's work for long distances with almost the same precision, but the price is almost astronomical. So if you also connect it with some future commercialization or actual commercialization potential, so this device is not acceptable for the serial production. So this is the reason why everyone is searching for another solution. The solution which is close to this laser tracker is total station. Total station is some device because it's a complex sensor. Here we have one on the screen in the picture, which are used by geodetists. This device has some advantages, some disadvantages. I mean, one of disadvantages is some, let's say, connection with the printer, because you need, for example, the visibility of printing head during the wool process, and so on and so on. So you have some limits where to place this device, and so on. Then there are, of course, some radar distance measurement. They are relatively robust, mostly used in cars, vehicles. You know it from your lives. I mean, one disadvantage is the precision, and of course the distance where they operates. Then some ultrasonic sensors. It's some similar problem. So mostly the final solution, and also our solution of the problem, is LiDAR. We use in our application two-dimensional LiDAR is enough for our purpose, and it allows us to hold the adequate ratio between quality and distance, so between precision and measured distance. I sorted the navigation or localization or measurement problem into categories divided by the construction of the printer robot. I am not so great, let's say, in this dividing like Jan was. So I selected only 3 main categories with the, let's say, main potential, and with some significant marks in navigation. The first is a gantry construction. The gantry construction is using some standard navigation solutions, because it's also standard industrial construction. You know it from some cranes, for example, and so on. The really big advantage is that all movements are in 1D. How to understand it? If you look to this this picture, which is from Digital Trends, we have here the moving of the wool frame in this way. So it's a measurement of a distance, and you always know where is the point which you want to measure. And then there is the printer head. It's is here now. It's in some parking position. Of course, the printer head can move inside this frame. So it's something like a CNC machine, and you are operating in this in these 2 dimensions. And once more again, the task is really simple, because you have here inside the frame some servo drives which allow you to really precisely measure the actual position. So it's not a problem to show or to define where the printer tool is actually on the construction site. So your measurement is not dependent on the distance. Yeah, it's with the same accuracy for long and also for short distances. On the other hand, it's a open space, so you can count that there can be some weather influence, but with the right sensors, the weather influence can be minimized. You can use also some magnetic sensors, maybe instead of laser sensors or the incremental sensors inside the drives. Yeah, so you have really a lot of possibilities how to do it. The disadvantage of this approach is, of course, the construction itself, because you need always to be outside the final house. Yeah, so you are limited with the object which you want to print. The second category which I want to show you, and where I want to spend some words about the navigation, is a robotic arm system. It's a really nice combination of the actual technology used for some new production, new type of a production. What does it mean? You have a really standard industrial robot which realize all the movement. Industrial robots, of course, is known that the navigation of the tool is solved. And because in industry, it's a standard task for the robot to hold some trajectories with really high precision. So it's not a problem. Once you use the sensors which are inside the robot, so everything works perfectly. But on the other hand, there is one disadvantage of the VU solution. And the disadvantage is also possible to see on this picture. You need to hold the robot in one position, because once you move with the robot, so you need to localize it on the construction site. And for such a type of robotic arm systems, it is a really challenge to do this new setting. Another problem can be what is the space where you can realize the printing. I mean, this technology is really close to the third one, which I have here in the presentation, is the SCARA construction. The SCARA construction is the similar one to the robotic arm. Of course, the main difference is in the positioning of the printing head. Now you are not moving like an arm, but you have here some axis, and you are doing this rotation in axis. Of course, you are able to move it up and down in this position, or sometimes it's possible to do the moving here in this position. So you can use, once more again, some sensors in drives. If you have the construction with the right quality, so it's not a problem to do it like or to use such information from drives. But once you have the construction which is light, and if I to sketch it, so construction which can be something like this. So some arm, of course, here you need some nivellation and the printing tool in this position. So from the analysis, static analysis, we know that on this length, which with higher length, you need to fight with the problem that the final point is moving down. Yeah, this point is changing the position. It's not in the same on the same level like this one. It can be problem in some cases, and you need to measure it. Moreover, the length of the arm, you can see, is changing because you have here this rotational axis. This SCARA construction is the construction which is used in our project. So we believe that the sensor in the drives will be enough, but our motivation or our aim is not only to hold the wool robot, wool machine in one place, but we want to move it on the construction site. So this is some type of a challenge. As I thought in the beginning, I have here also some systems which I mark as exotic. You can see one exotic system here on this picture. And what does it mean? These solutions are really special, usually covered with a lot of patents, but with a really questionable commercialization and with questionable application. The movement of the wool robot is complex. Sometimes it's moving the wool robot with the printing end. So, for example, in this case, there are really specific requirements for the concrete because it need to hold the wool robot. Sometimes it's navigated by some line, so also some specific construction. It's question of the future if there is some potential for this type of robots for 3D printing of buildings. So our solution of navigation is, or generally the solution is SCARA construction, as you saw, and we have two tasks in navigation. The first is to find the robot position on the construction site. So let's say we have here some axis, so to find in some axis system where we are now with our robot. And the second task is what is the position of the printing tool in the same axis system. Maybe I will do it better because the axis system is usually in such a way, so it's fixed to the construction site. So the robot is not placed in the center. It's not in the place 0, 0. It's somewhere. And once you want to move with the robot, so you need to know where it is. You can see that we don't have actually in our first version any wheels which allow us to move it, but you can move it, of course, once you finish some part of a task. So the robot and the machine, the printer, can print buildings which are bigger than is the actual ratio of the printing tool. What are the challenges? Of course, the precision. It's the main question because we need to be enough precise, also in short and also in long distances. Why in such a big scale? Because in a short distances you need to be precise for a printing tool. Yeah, the printing tool distance from some center of the machine can be in some scale, let's say half meter to 5-6 meters. So in this short distance, you need to hold some precision. Our aim is be under 5 millimeters. It seems it will be enough. Why long distances? Because once you are on the construction site where these distances are in order of tens meters, so you need also to know where exactly is your robot, and the robot can change the position in the system. Of course, it's possible to use not only one measurement system or localization system, but some combination or two of them. Our aim, our actual way of development is use only one. You can see it here in the picture that we are using some LiDAR. It's something what I can mark as a compromise solution, because it serves us good precision, and also it's accessible with say low price, or acceptable price. As I thought, we have two main tasks: localize the robot in the construction site, and find the position of the tool. For these two tasks, we use only, or want to use only, one sensor. It's I mean, the innovative approach and the biggest challenge. What is the idea? For the localization, we use the radar. It is LiDAR with focusing on some targets. Actually, we count with 3 targets on the construction site, which will be placed by a geodetist with a right angle, and these targets, if are highly reflective, so it's easy to localize them in the surround with the software which is inside the LiDAR, so it's not a problem, and with really acceptable precision. What is the advantage? Once we move the robot to another position, so we can use the same target, so it's no need to change anything. Moreover, the targets can be over the construction, because if you count that you print the walls of some house, so let's say the wall is 3 meter height, so the targets will be in some level 3.5 meter, which is still reachable with this LiDAR on the top, as was showed on a previous slide. The second task is the tool position, where, to be honest, we believe that our construction will be the right one, and will be enough to use the information from a sensor, from the servo drives. But we are also prepared to realize the task of positioning of a tool by the sensor, simply to XY coordinating system without any problem, because one, we have some reflection point in the line of the beam from the LiDAR, so we are able to detect this target, and with the information about the angle and the distance, count what is the actual position of the tool of the printer. This that coordinates, so the height can be then measured by some external sensor. It's not so huge problem. Here I have some, let's say, result which we have from some proof of our concept. The LiDAR is SICK navigation 350 with such a characteristic. You can see that the precision by datasheet is in the range 4 to 25. Independence on the target type. So with this high reflective target, we are under the value of 4 millimeters. Our actual precision or deviation is around 3 millimeters. So it's really acceptable for us. And moreover, we find that the wool solution is robust because it's also important question for the wool task, wool machine, and all sensors. You can imagine how it is on some belt. There is some dust and so on, some influence of a weather. So we wanted to cover the head with some tube, and it's fortunately not a problem to do it. So this seems like the right way how to realize the measurement in our case. So this is the last slide of my side, and now I will skip my presentation, and the final word will be on Jan.
Well, thank you, Lukáš. I will turn on the presentation. I would like to complete your notes or your information. We don't use pure SCARA system. As you saw, it's an enlarged SCARA system because we'd like to print behind the corner also, and there are also missing some parts on a printing heads which enable us to print two corners. So we'd like to print behind or to go around obstacles, let's say walls, and we like to print in continuous from different printing positions and to print continue wall. And another information I would like to complete. We don't use only one sensor, so it's there are lots of sensors mounted on the robotic systems, because from the control strategy we need and localization, we need information from the distance from the ground, for example, and the influence of weather and thermal influence. So, for example, how the arm is bended, or if the mobile platform is good leveled. So there are these sensors for auto nivellation, or to get information about shrinkage or bending or something like this. So that's why I would like to mention that we don't use only one sensor. Well, I would like to skip test results. Well, So we are approaching to the end of our presentation and seminar. So let me summary the presentation, our talk, and then we can open discussion. So I presented our project called 3D Star. Then I presented in general the 3D printing technology used in civil engineering or in architecture and construction. So these large scale 3D printers. Then I briefly present our contemporary results from the project, and then we switched to we changed presentations with Lukáš, and he present you our task, so navigation of this robotic systems, navigation and localization of these robotic systems, and shown some semi results. Well, what you can see on the right side, as I mentioned at the end of my part, the level of automation in construction number 5 doesn't exist yet, but there are already some projects. For example, here is presented one project from ESA, so it's a space agency from European Space Agency. The same has or similar has NASA and other space agencies. They would like to build this independent construction robot. So this one example. They would like to somehow sinter or glue moon dust or regolith with special liquids, and independently without any remote control or with the help of operator. So no, and this is the end of our presentation, and I would like to open the discussion. If you have any question or notes, you can ask, and we will appreciate for any feedback. Well, if you have no question, I would like to inform you that this presentation will be accessible from online via these links of the project R2P2. It's going to be also online on a YouTube channel, so it will be accessible. And if you have then any questions, so we are reachable on our emails or via these links. So now is short time for a question. If you have no, doesn't matter, but we are still here. Well, I wouldn't like to disturb you or to make a longer our seminar. If you have no questions or notes or feedback, let us say thank you for your attention, and hopefully we will see during the next seminar maybe from the project 3D Star or from in the frame of project R2P2. And well, thank you for your attention and have a nice day. Goodbye.
Goodbye.